what do we mean by multi-agent environments? We have actually discussed, agents already, so we know what they are. They are independent entities. They know about their environment. They take input from their environment, process the information, and then take appropriate action. That's how we define a general agent. We also discussed about rationality and so forth. Now we're going to talk about multi-agent environment. And what do we mean by multi-agent environment? Okay. In these kind of environments where every agent, more than one agent, of course, and every agent needs to consider the impact of the decisions taken by the other agent or agents. And the most common example of this kind of situation is traffic, for example. You're driving a car, you're not alone by yourself, right? So when you're driving a car, you have to take into account the actions of other agents, human beings, machines, and so forth. So you need to be aware of what is it that they're going to do and then act accordingly. That's a general kind of concept, so you understand what we mean by multiple agents and their impact on the performance of each one of them. So an agent is actually has to be aware of its own welfare, okay? And to be able to do that, it must know how the other is going to react. Now, these situations can be quite unpredictable as well. Once again, traffic situation. You don't know the oncoming traffic, how they're going to behave. Or in fact, not just that, the other agents that may be in front of you when you're driving, you don't know how are they going to turn right. Sometimes people make mistakes. So there is this certain amount of unpredictability in multi-agent environments. And this can create contingencies, unknown situations for which the agent has to be prepared for. Okay, so that's what we mean by multi-agent environments as well as competitive environments. What do we mean by competitive environment? Okay, and this is typically situations where, let's say previously, we have seen search examples. In search, so far that we've discussed, you are the only person there. It's a one-man show, and you're trying to find. The mouse was trying to find something. The child was trying to switch on light, right, and so forth. So, and you were trying to traverse, let's say, a tree, finding a solution. So you were all alone by yourself. Multi-agent environments is that there are two people actually sitting opposite to each other and trying to move and search, and a person on the left may have a different goal as opposed to the person on the right, and they have opposing targets to achieve. Okay, and this kind of arrangement discussed before, maybe I mentioned, is called you have these are your opponents, and opponents, in other words, are your adversaries. Okay, so this leads to what we call as adversarial environments. Typically, it happens in games. So in general, one man or single person search, okay, there's no opponent. Your solutions are based on typically heuristics, rules of thumb that tell you, let's not try everything, let's make an educated guess and move along. So sometimes that will work, sometimes it won't, but most of the time you actually do it. We are doing it now today, everybody 24/7. Okay. And heuristics, of course, and constraint satisfaction problems, which are trying to meet everybody's requirement. You may recall very early on I discussed the creation of a timetable, okay, of classes in a university environment. You have to meet the constraints, the limits of each and every player in that. And there can be students, there could be teachers, there could be classroom availability, and so forth. Okay, so that is what we mean by constraint satisfaction. Let's talk about something else also, and that we're going to use again and again. Evaluation function. When you're looking, let's say, on a chessboard, okay, and all of you're trying to plan something, you are scheduling something just like this timetable, okay. So you have to, what you want to do is, you want to know the traveling distance. How many steps will you require to get to your answer, your solution, okay. Now, how do we assess that the move to the right or the move to the left or move straight on or moving backwards, how good or bad that is? I think we have already seen some of that as well. You know, the remaining distance, I discussed that. So that function that evaluates helps you understand that you are moving in the right direction will depend on a function that is, trying to do something, gives you a value, and higher the value of that function, you say, all right, I will choose this option as opposed to the one which gives you a smaller value of that function, okay. And planning, scheduling activities and so forth. In games, for example, the evaluation function also does the same thing, but the result that may be good for me of that from that evaluation function may not be good for my opponent, right? So every time I want to make a move, heuristic function, evaluation function will actually tell me that for me as a player on the left, moving to the right is a good option, but for the player on the right, okay, it may just be the opposite. So every time I make a move, I have to evaluate the evaluation function, the results of that. And also, as a strategy, I also try to preempt my opponent's move as well. My opponent is my adversary. I'm trying to, in chess, I'm trying to kill its king, and he is also trying to do the same. So first of all, I have to understand, how I am going to do it, as well as defend myself against the other. Okay, so that's a very interesting situation. And that's why games are so interesting. So many people are interested. And of course, then sometimes there's a time limit. Once again, talking of chess, you have to make a move within, let's say, 2 minutes. That's it. Otherwise, you lose a point or something. That's the rules. So you have to come up quickly enough to be able to make the right move. Okay, evaluation function, as I said, tells you the goodness of the position of a chess board or a tic-tac-toe. Remember that game? Noughts and crosses, some people call it. So that position of the problem or the solution space will depend on the goodness, and I need to make a proper choice. So chess, checkers, Othello, backgammon, and so forth. There are two types of kind of extreme I just want to mention: multi-agent environment. There's something called cooperative, okay, environment. You have the same utility function, okay, to be able to make your choice. As opposed to, there can be competitive environment in which one agent can only win when the other loses, sometimes called zero-sum games as well. Also, just passing reference to mathematical game theory, it's a branch of economics which views multi-agent environments, human beings, as a game. And it says, provided that the effects of the agent, of one agent on the other, if that is significant, then mathematical game theories can be applied to economics as well. Now, regardless of whether the agents are cooperative or competitive, every agent decides to do based on its own utilities, but it all must also interact with other agents as well. Okay, agents typically act strategically. Okay, when it decides to move, and we have said nature itself is a strategic agent, though we can't really predict how nature works. By the way, as is normally said, there's a method to the madness, okay, meaning that nature, to us, since we don't understand nature, sometimes we say we don't understand why it is happening like this. But there is some method to this, because nature was not created just like that. So it's a special agent. Sometimes people call it that it's more statistical, whether it's going to rain or not. Okay, it's going to be windy or not. We have some perfect information and imperfect information. In perfect information, things are very deterministic for every agent. Everything is observable, fully observable environments in which the two agents act alternatively, and in which the utility values at the end of the game are always equal and opposite. So one winning, the other losing. I get 10 points, I gain 10 points, he loses 10 points. I gain 5, he loses 5. So it's like a kind of a seesaw thing. And once again, in chess, as you know, if one person wins, the other necessarily loses. Of course, there are deadlock situations as well, right? That's when they say that the game is a draw. Most of the situations, one loses, the other wins. And in AI, typically, what's important is the representation scheme as well. Because what we're trying to do is we're looking at people, let's say, playing these games, chess, backgammon, noughts and crosses, people call it tic-tac-toe, and so forth. Okay. So what's important is that AI is trying to actually think of ways of representing these games so that we can work on them in computational terms. How can we computerize these things? Okay. So that's what fundamental AI is all about, trying to find a good representation that can then be translated into computers and then help you solve those problems or games or play games as machines do against human beings. So I guess this has been interesting. You should have liked it. Thank you so much. We'll see you again.